stomach app. I'm not sure when I need to run for the toilet, so be ready. Okay. Hopefully I can stand for the 2 hours. So before we before we how to say dismiss, please remind that we take a group photo. Okay, see, yeah, okay, for the last day of the class. See how many of you survive for the class. Okay. I think I need to go soon. Okay, before I go to the toilet, let us discuss one question first. Okay, so let's do this question to remind ourselves what the surface integral is. So try and evaluate this function z. Okay, this is a double integral. Okay, but the double integral here have a dx. Okay, not the normal dA. So this surface is not flat. Okay, so what kind of surface is this? So this is a surface that built up by three sides. Okay, S1, S2, and S3. Okay, S1 is the side, S2 is the bottom side, S3 is the top side. Okay, and the side is covered by a cylinder. Okay, you should start imagining you have a cylinder. And what's the radius of this? S squared plus y squared equals to 1. So you should start imagining a cylinder. And then x2 is a disk. Okay, as a disk satisfies x squared plus y squared less than or equal to 1. What does this mean? This means I have, when it is equal to 1, I got a circle with radius 1. When it is less than 1, meaning I take all the points within the circle. So I fill out the disk. Okay, so draw up what I'm talking about. So first you have a cylinder, infinite cylinder, right? Then second, with radius 1. Yeah, with radius 1. Second, you have a circle, okay, with radius 1, and then you take everything inside. Less than equal to 1. In the plane z equal to 0. Okay, so meaning on the xy plane. Okay, on xy plane. And then top part is what? The top part is the plane z equals to 1 plus x. What is this? This is a plane with normal vector 1. What's the normal vector of this plane? 1, 0, minus 1. Okay, so if you rewrite this into x minus z minus 1, okay, you got the normal vector 1, 0, minus 1. Okay. It is okay if you pick minus 0, minus 1, 0, and 1. Or you take the negative of it. Just the difference in the direction. Okay, but both vector will be perpendicular to the plane. Okay. So if you take 3 of this, cut it off, you will get something like this. Okay, you got a plane like this. So here is the vector 1, 0, 0. Like this. Is it like this? Okay, I think if I point it in this way, the other one should work. Okay. 1, 0, minus 1 point the other way. Okay, no. Okay. So how to do surface integral on this kind of surface? So you have 3 surface here. 3 surface intersect at finite number of curve. Okay, so you can use the additivity of the integral. Okay, so you can split the surface into 3 parts. Okay, so let's write our surface to be x1 union x2. Should we put x1 union? Yeah, x1 x2 union x3. This Not very precise if I write this. Okay. Very precise if I don't write this. Do you see any problem if I write like this? Because this cylinder is supposed to be an infinite cylinder, but we want by this plane here. Okay, so we need to introduce some restriction to this cylinder, right? Okay, so we need to redefine our x1, x2, x3 actually. So what is x1? Okay, x1 is a cylinder. Okay, it's all the xy that such that x squared plus y squared equals to 1. And then what? Uh, and then and then what? But it is cut off bottom by what? Bottom by the z equals 0. Okay, so your z must be greater or equal to 0. Okay, but the top part here is bounded by what? So bounded by this plane here, right? So from 0 all the way up to this plane. Okay, what's this plane? So z is bounded above by 1+x. Okay, so this is actually the x1. Okay, so this is what x1 precisely should be. Correct. Okay, so it is part of the cylinder, but the z is bounded below by 0 and bounded above by the plane. Make sense? Okay. Yeah. How about x2? X2 is easier. S2 is what? Yeah, S2 is the bottom side. So what's the bottom? Bottom is the disk. Okay. Yeah, it's the disk s squared plus y squared less than equals to 1. How about z? That is equal to 0. Okay, lying on the xy plane. How about S3? Okay, S3 is a bit uh, interesting. So what is S3? Z equals to 1 plus x. Okay. Then how do you control your x and y? Still a circle? Hmm. How to describe this? Uh-huh. Yeah, so what's this x and y I have to satisfy? So if you remove the height, what are these x, y actually? Also the this, okay, also this x squared plus y squared less than equals to 1. Okay, so meaning what? Meaning this z equals to 1 plus x, you can think of you are elevating the disk. Okay, no, elevating the disk. So you give height to every point in the disk. Makes sense or not? Okay, another way to think about it is if you project this slanted circle down, you will get this with radius 1. If you just project it down. Okay. Okay. So the plane, so this z equals to 1 plus x somehow elevate this for you. Okay. Okay. Actually, all the xy here satisfy the disk of radius 1 equation. Okay, you forget the height. Make sense? Okay. Okay. So using the additivity of integral, okay, we can split the integral into 3 surfaces. Okay, so one is x1, one is x2, one is x3. Okay. So note that this function here, right, really only depend on z. Only depend on z. My scalar function here really only depend on z. Okay, it doesn't really depend on x and y. Okay, because due to time constraint, maybe we just pick one of them and do. Which one do you want to pick? S1, S2, or S3? S3. Okay, you want to do S3? Sure. Okay, let's do S3. The other will follow similarly. Okay, so what's the criteria to do a surface integral? You need to parameterize your surface. Okay, like how you parameterize your line, right? Because here there's an x, y, z here, but here there's only double integral. Okay, how to put 3 variables into 2 variables. Okay, this is a surface, so we can use 2 variables to describe the surface S3. Okay, so how should we reparameterize this? Okay. So how should we reparameterize this? Yeah, how should we reparameterize this? So let's call it R3 maybe. Okay, we have an XY variable here. Can we control this XY so that I can find all the point in my X3? Is there a way to do it? So look at what equation S3 has to satisfy. Let's zoom in. So look at what is the equation that S3 has to satisfy. Any condition on X or not? S squared plus Y squared less than or equal to 1. Okay. Y also satisfy that condition. Okay. But Z is dependent on X only. Okay. So can I extract 2 variables to make this parametric equation? So if I let Z equals to 1 plus X, surely I have X on the X part. How about Y? Square root. Uh, okay. So what do you want to do? You want to put square root what? 1 minus x squared. Then you make everything into 1 variable. Right? Become a line. Become a line already. Fair enough. This is a line. Right? You need 2 variables. Okay, so you need to move in the other direction. Okay. So you need to make your y free. You can make your y free. Okay. But by doing this, you still remember that there's something controlling the x and y. Right? So how do you control x and y? This will become the domain you need to fix. Okay, so your x and y is a point in the disk. But we can change variable, right? Okay, we can change variable. Change it into a polar rectangle equivalently. Okay, depend on which one is easier to do integration, later we will use it. Okay, does it make sense? Okay, okay. So in your parametric surface, make sure your parametric equation have 2 variables. You cannot draw a surface. Okay, you need to have two linearly independent variables. Okay, so so okay, so to compute surface integral, what do you need? You need. So in the line integral, you need the length of your tangent vector. In surface integral, you need the length of the normal vector, okay, of the tangent plane, right? Okay. So how to get the normal vector of your tangent plane? So from this parametric equation here, there are two variables here. Okay, two variables here. Two variables here, you can do what? You can do two tangent vector, right? You can do partial derivative with respect to x and partial derivative with respect to y. Okay, so you can get two tangent linearly independent two tangent vector here. So first you get 1, 0, 1. Okay, second you get 0, 1, 0. Okay, so we are using technique from partial derivative, right? So if you cross these two vector, what do you get? What do you get? You get, do I write out the step for you? IJK 101 0 1 0. Okay, so what's this? So you should get -1, 0, and 1. Okay? Yeah. Okay, what else do we need? What else do we need? So we need the length of this guy, right? We need the length of this guy. So what's the length of this vector here? So the length of this vector should be square root 2, square root 2. Okay, so recall what's the definition of a surface integral? So we change variable to d. Okay, we change the surface to a two-dimensional domain, which is the d3 we fix here. Okay, we fix the d3 here. Okay, fix the d3 here, and then what? Then my z will become what? My z will apply on the parametric equation that we have on z, which is 1 plus x. Okay, multiply by. Okay, so let me write out the general form first. So z apply on rxy. Yeah, z apply on rxy, and then we have the length of Rx cross Ry, and then dx like this. So this is the formula. And let's continue. Keep this in mind. Okay, and then so we sub my function z in terms of the z I have, which is 1 plus x times square root 2 dx. Okay. Okay. All right. So what to do next? So this is what you learn in the multiple integral. Integration of d dA. Okay, just now you see. So here is the difference. Very important. Look at here. Look at this surface integral here. Very important. See here. This is d capital X. Here is d capital A. What's the difference? Yeah, what's the difference? D capital X is a curved surface. D capital A is a flat surface. Okay, so general curved surface we use D capital X. And then we do this parametric equation here to change the curved surface to the normal flat surface. Make sense or not? Okay, make sense, huh? Question. Okay, this is very important key. This dx and dA, you must know how to go from dx to dA. Okay, through parametric equation. So you have a curved surface, right? You make it to flat. So you have a Jacobian factor. What's the Jacobian factor here? It is the length of the normal vector of your tangent plane. Okay. Now, if you're gonna do here, see here this function in terms of x. But we know that we need to integrate over a disk. So we want to do it in the polar coordinate. So in the flat surface, we want to do change variable again. So we need another Jacobian. So we need another Jacobian. But this Jacobian I already computed for you, which is, so yeah, which is if you want to change from the rectangular coordinate to a polar coordinate. You see. Okay, so here we get square root 2, integrate from 0 to 2 pi, 0 to 1 of 1 plus. So x in polar coordinate is what? R cos theta. And then multiply by half. Okay, dr d theta. So you see, this is what I said yesterday. You introduce two Jacobian here. Okay, first Jacobian is go from the curved surface in 3D to flat surface in 2D. And then the second Jacobian is you change variable in the flat surface. Okay, no? Yeah. Okay. So in the flat surface, remember why we introduced the Jacobian for change of variable? Because we kind of stretch the normal flat rectangle, okay, to some polar rectangle, for example. Okay, so that's why we have the Jacobian there. And you actually can check that you use the same construction to find the Jacobian there. You also take the tangent vector, the normal vector of the tangent plane there, and then computed the length. Actually, this R is obtained that way as well. Okay, yeah. Okay, no. Okay, so this integrate out will be a square root 2 of pi. Question? Okay, there are S2 and S3 here. Do you want to try and do it? S2 and S3? Right? S2 and S1, yeah, S2 and S1, yeah. Do you want to try and write down what's the parametric surface and then try and integrate it? Then I go to the toilet for a while. Yeah, I think see you after 5 minutes. I go to the toilet first. I'm back. Happen to go up. Huh? Despite. Yeah. Okay, so let's start with parameterizing x1. What should the parameterized surface for x1 be? Huh? Any idea? What's the best way to parameterize the x1? Using two variables, right? What kind of variable you want to use? Huh? Theta and z. Why would you use theta and z? It is part of the cylinder, right? So cylinder is circle. So it's just circle. And then the radius doesn't change, but the height will change. Okay, so you just use angle and the height. Because radius doesn't change. Okay, so we will use the theta and z. Okay, so the xy direction we will use cos theta and sin theta because this is the cylinder, the side of the cylinder with radius 1. Okay, usually you will put radius times cos theta and radius times sin theta, and then with the height. Okay, with the height z. Okay. So in this way, we make it into a flat surface because the domain here is just theta and z. Okay, so theta is from 0 to 2 pi. Z is from 0 to 1 plus x. So x in this case become 1 plus cos theta. R cos theta, but R here is 1. Yeah. Does it make sense? Okay. So here is R1. How about R2? R2. Yeah. So S for S2. Okay, so for S2, what's the two variable that you need to describe this X and Y? Okay, X and Y. So how are you gonna use X and Y here? So it's what? You mean it's just X and Y, is it? Okay, and then the Z is always 0. Okay, but if you do this, you need to fix your X and Y. Okay, so what's the X and Y you fix it? Only those X and Y that satisfy this equation. Okay. Okay. So similarly, you can do change of variable for this right. You can do it. You change it to radius and theta. Let me write for you. So, so you use the knowledge from the multiple integral. I can change variable for d2 to r theta, so that I integrate from 0 to 1 for r and 0 to 2 pi for. Make sense? Okay. Yeah. So you can see that this D2 and D3 are really the same, right? But what's difference is the height. Is the height different here? Okay, is the difference in height. Okay. Okay. But this height here doesn't affect your domain you use. It doesn't affect the domain. Okay, no. Did anyone manage to finish calculate the integral? Okay. If not, you try it out. So follow the same method. Compute Rix, Rij, cross them together. Okay. Find the length. Okay. And then compute the surface integral. Okay. Is it okay? Anyone computed? Yeah. Yeah. The integral of x2 is 0. Yes. Why? Why can you directly see that the integral of s2 is 0? Why? Yes, correct. So why s2 has integral 0? Can you see directly why? Because z is 0. And then the function you integrate is z. Okay, z is 0. So integrate over 0 function. Okay, 0. Okay, no? Okay, yeah. So the only thing you need to compute is R1 now. Okay, please compute it. And then you can check my answer later. Or anyone computed R1 yet? No? Not yet. Okay. Okay, let's go on. Keep going on. You cannot stop, right? Okay, so next we'll talk about the orientation of surface. So last time I talked about plane, right? How many orientation I can put on plane? Okay, there are two of them, right? Going up or going down. Okay, so we need to pick orientation. Like just like last time we do line integral, right? When we have a curve, we know where we start, where we end. On surface, we need to put orientation on it. Okay, compatibly. Okay, compatibly. So what do we write here? So uh, so we need to introduce orientation compatibly. So what do we mean by that? So let's consider this Mobius band. Okay, what is Mobius band? So you take a strip. Okay, you take a strip, and then you close it out like this, right? What you get is just a cylinder. But if I turn it, twist it on one side, and then join it together, this is what we call a Mobius band. Okay, this is what we call a Mobius band. 比乌斯网. The Chinese name is very great. Okay, Mobius band. Yeah. Let me join it. Okay, so we will say that this Mobius band is not orientable. Okay, why is it not orientable? So let's say we fix a point here. Okay, we fix a point here. And then I choose an orientation. I can choose one, going up or going in. Okay, I choose one. I choose going up, let's say. And then I walk along this Mobius strip. And you see, I walk, go inside. Okay, I go inside. Actually, I come back to the same point at this point. But the orientation changed, point inward. So we cannot make any choice such that this orientation can be made compatibly. Okay, so this surface is what we call is non-orientable. Okay, it's non-orientable. Okay, you can try and play around with it. I pass it around. You can play around with it. So I make a dot. So I make a dot on both sides. You can try and walk around this Mobius band, and you cannot fix orientation of this point. Okay, no matter how. Compatibly. Okay, yeah. You can pass it around. Okay. So from now on, we only consider orientable surfaces. Okay. So either on the surface, or the point I put outward, or all the point I put inward orientation. Okay. So yeah. So then what we like last time what we say, we don't only just consider the normal vector, we consider the unique normal vector. Okay, let's see how this unique normal vector comes into play. Okay, you can try and derive this. Okay, if your surface is some z equals to fxy, okay, you can try and see why from this general formula here you will get this specific formula. For z equals to fxy. But the most important thing is this formula. We will use this. Okay, I don't care the specific one. Okay, I just care the most general one. Okay, but as an exercise, you can try and deduce this. Okay, if your z equals to fxy, how do you deduce this specific formula here? Okay, and because this specific formula here is kind of interesting, if the k component is positive, then it will give the upward orientation. It will give the upward orientation. Okay, if it is negative, then it will give the inward orientation. Okay, and one exercise you can do is you can apply this, check this on the sphere. Okay, check this on the sphere. For example, check it on z equals to x. Sorry, so z. Okay, just pick this one, square root 1 minus x squared minus 1 squared. Okay, check it on this, and then try and draw this end up. Okay, make sure it is upward. Yeah. Sure, you can take a stapler. Yeah. Can you reconstruct it or not? Yes. Yes. Okay. Yeah. Try and compute this. Okay. So, like last time, when we do line integral, we're interested in the loop integral, closed loop. So, like surface integral, we also interested in closed surface. Okay, we close the surface out. So, for example, what's a closed surface? A sphere is a closed surface. Okay, close up. So why is it closed? Imagine you are an ant working on the earth. You can never work out the earth, right? Okay, you just keep working, there's like no boundary. Okay, so it is closed. Okay, there's no boundary you can see. Okay, if you work on it. So it is closed. So on the closed surface, there are two kinds of orientation. One is outward, is like deviant, right? Okay, the other is inward. Okay, so there are really two kinds of it. Okay, outward and inward. Okay, so how are this important? How is this important? So we introduce surface integral of vector fields, okay? Of vector fields. So remember, we only know how to do surface integral for scalar field, right? For scalar field, we already know how to do integration. So how to do integration for vector field? So similar to word done. What happened in word done? You have f dot x. Okay, you dot the two vectors together. Now you also need to dot two vectors together. You dot the vector field with the surface together. Okay, ds is the surface. Okay, you dot the surface integral, the surface with the vector together. Okay, or not? Okay, so the result of this is you will, so in the line integral, when you dot them together, you have the tangent vector. But in the surface, you will have the normal vector, okay? And the unique, which we have this as the unique normal vector here, f dot n. Okay, you need to, this is by definition. Okay, this is by definition. Okay, this is by definition. And this is what we call a flux. Okay, magnetic flux and so on. This is the flux. Okay, so in line integral, we only dot vector field with line. Okay, but surface integral, we dot vector field with surface. Okay, so meaning we want to integrate every how to say, every height on the point on the surface. Okay, yeah, we want to try and add up all these contributions together. Does that make sense? Yeah, we want to add up all the contributions together. What is vector field? On every point, I have a vector. Right, on every point, I have a vector. Okay, I want to add up all the contribution of this vector together. This is what the surface integral does. The magnetic flux, right? You want to compute how strong is the magnet. Okay, you want to add up. So like every part of the magnet is like trying to attract something, trying to repel something. Correct? Some part of the magnet is stronger than the other part. Okay. Makes sense? Okay. Yeah. So this is the definition. So if you want to compute a surface integral of a vector field, okay, not a scalar field, it's a vector field. So previously we have a scalar field, now we have a vector field. Then we need to dot with the surface dx. Okay, this is equal to the surface integral of f dot the unit. Oh, let me label this unit normal vector. Okay, so if you dot these two vectors together, you get what? A scalar. Okay, so this becomes a scalar field. So that's why you see there's a both x and a normal x here. There's a both x and a normal x here. Okay, what does this mean? Both x here means the parametric equation. So I mean, so it looks like this. So xt, so dxt, d yt, dzt. Okay, change in x, change in y, change in z. But after you dot it, then so this is the dx plot. Then dx will just become dx dy, something like that. Dy, yeah, dx dy. Or should I change variable? Okay, let's change it. So maybe become dp dq or dr dx. Okay, just use dr dx. Okay, two variable. Remember? So our surface is in 3-dimensional. Okay, so we have 3 coordinates to explain it, but after parametrizing, we just need to use 2 variables to describe it. Okay, maybe use dr dt, otherwise too many x later. Okay, yeah. Okay. Any question about this? So maybe let me write down one more line. Maybe it's easier. So R PQ equals to S PQ Y PQ and Z PQ. Okay, so shouldn't just be T here. It should be PQ. Okay, yeah. So this is the parametrized surface. So when I talk about this, right, you should really recall this example we do just now. Okay, recall the example we do just now. Okay, we parameterize the surface into 2 variables using 2 variables. Okay, so you need to differentiate between both x and normal x. Both x is something in 3-dimensional. Small x is something in 2-dimensional. Okay, so that this integral here will match. Because you have double integral, right? You should only have 2 variables. So what happened to the vector? Okay, you dot it with the unique normal vector. And you dot it with a unique normal. No worries, later we'll do example, okay? Just believe me first, and then I will convince you later. Yeah. The says is not ball is still a circle. Yeah, yes. 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 Yes, 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 yes. You are right. So what's the next step here? So the theorem is like this, okay? So instead of multiplying, instead of dot with the unit tangent vector, you just need to dot with RU cross RV, okay, to go back to DA, okay? Yeah. So what is this line here? So this line actually not so complete. So what is the relation between UV and parametric surface. So this is for parametric surface S. Okay, so what's the relation between S and R here? So what is X? So you need to parameterize your S by RUV. Okay, RUV. Okay, where UV is in the D. Okay, no. So how is this derived? How is this derived? So let's prove it. Okay, let's prove it. So here is also a specific cases. Okay, when z equals to fxy, you can try and derive yourself. But what is important is the first line here. Okay, first line here. The general one is more important. Okay, let's derive this. So let's start with the double integral of vector field. Okay, so what's this? This is by definition what? Just now we say. So this is by definition of the double integral on f dot with the unique normal vector. Okay, and then dx. So if you want to differentiate the 2x, you put both in the other one. But what is this? So just now, how we make a curved surface into flat surface? There's a Jacobian factor there. What is that? Huh? The normalized? Not the normalized. The what? The length of the normal vector. Right? The length of the normal vector. So you need to multiply f. So you need to change this to d dot f n bar of multiplied by ru cross rv. Yeah. Okay. But what is n here? What is n here? N is a unique normal vector. So meaning what? So meaning this guy is ru cross rv divided by the length of ru cross rv. Right. Okay. But you have extra contribution when you make the curved surface flat. Okay. So you can see that this length function here cancel. The norm here cancel. Okay. What you left with is just integration of f dot with the cross product of ru cross rv. Yeah. Okay. 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 So this is a little bit different from you do the surface integral on scalar field. On scalar field, you need to multiply by the length of the normal vector. But here, you take your vector field dot with your normal vector. Okay. Because remember, here vector field is a vector. Okay, you want to integrate a vector, how? You cannot integrate on a vector. Okay, if you integrate on vector, the answer you get is a vector. But magnetic field, I want to get a number. Okay, so meaning you need to make your vector into a scalar first. So how to make it into a scalar? You need to do dot product with some vector. So what's the vector you take here? You take the normal vector. Make sense? Okay, so this is the difference between the two. Okay, let's do example to make it memorable. Which example we should do? Okay, let's do this guy. Okay. Find the flux of the vector field. Okay. Zi, yi, zi plus yi plus xi. Okay, across a helicoid. And then they already give you the parameterization, so you should be happy. You don't need to do parameterization. So what do you need to do here? Okay, so what is flux? Okay, what is flux? Flux is equal to the integral of x f dot with capital dx. Okay, and then what does this become? Okay, what does this become? This becomes what? So by the derivation just now, this becomes the integral of d of f dot with the cross product, okay, or the normal vector. Ru, they use u, yeah, Ru cross Rv. Okay, so this is what you need to figure out. So you need to figure out what is d what is RU cross RV here. Okay, so let's figure out what is this. So we have RU equals to U cos V and U sin V and V. Okay. And then U is going from where to where? So let me put what's D? What's our D? So you need to tell me where my U and V lies. So U is lying between 0 and 1. V is lying between 0 and pi. Okay, so I need to compute what is RU. So what is R with respect to U? How should I differentiate? You get cos V, sin V, 0. Okay, how about RV? Minus U sin V, U cos V, and 1. Okay, so you cross these two together, what do you get actually? So RUV cross RV. Okay, so let me quickly write out the setup. So cos V sin V 0 minus U sin V, U cos V 1. Okay, so first term you should get sin V minus cos V and U. Is it? Check. Okay. Okay. All right. All good. Okay. So what's our domain here? So we're going from 0 to 1 for du. Okay. 0 to pi for dv. Okay. What's our f? F is z. So first is z. Our z become v. Right. Y becomes u sine v. Okay. And then z becomes. Okay. Did I do this wrong thing? Okay. So okay. So let me write down what is f here so that we can know what am I doing. So f y z here is what? Z, y, and x. Okay. But on my surface, the x, y, and z become a new parameter. Okay. So for my x, it becomes u cos v. Okay. For my y, it becomes u sine v. And then for my z, it becomes v. Make sense? Okay, so the vector field here would change based on my parameters. Because I need to apply my vector field on my surface. Make sense? Does it make sense? Okay. Any question or not? Any question? To dot with your cross product vector. Yeah, and then you do this computation here. And then the answer you should get is pi. Any question or not about this? So the new thing about this part, this chapter is you need to know how to parameterize surface. Okay, you need to know how to parameterize surface, and then you need to know how to fix your D. Okay, fix your domain for your surface, and then use the D, use the cross the normal vector to find your integral. Okay. Yeah. Okay, so this is the thing you need to do for finding flux. Yeah. Any question or not? Any question? No? Yeah. Okay, let's take a break. Let's take a shorter break, okay or not? Yeah, otherwise later I go late. Let's do it 2 until 2:10. Okay, let's break until 2:10. And we will see more, two more actually example. Okay, before we finish class. And for those who can't late, so make sure later we take a group photo before we leave. Okay, last class. Yeah. Yes, question. You mean for the R? By convention, we should put X, Y, and Z. Yeah, by convention, yes. Yeah, if this one you can change differently, then you need to tell me what is X, Y, Z already. If you change this X, Y, Z differently, then it's equivalent to changing the picture. Yeah. So I mean, by convention, we will fix X, Y, Z like this. Of course, you could change it, but you change here, change there, it should be the same. Yeah. Yeah, change the axis, that's what I mean. Yeah. You rotate the axis. Yeah. Okay. So we will finish Stoke's theorem and the divergence theorem in the second hour. Yeah. Until today content. Yeah. Stoke's theorem and no. After midterm. After midterm. Yeah, after midterm. After midterm until today. I think yeah. Anything after midterm. I already posted out the definition and the theorem sheets that you can have a look. Have you checked? I posted out the definition sheets you can get during the final. I posted out in the last column. There's a final exam column. And I posted out a practice exam question there also. Not practice exam question, but practice quiz question. Uh, yeah. Yeah, you can try out all those. Can find on in the final exam column. It's better you use that to do a revision so that you know what you will get in during that exam. Know how to use it. Okay, so let's start. Ready, boost up last hour. Okay. Okay, Stoke's theorem. So what is Stoke's theorem? So let X be an oriented surface. Okay, so you got a surface. Just now we said we want to orient it. Either every orientation go up or go down. Right? Okay, go up or go down. With a continuously varying unit normal n. Okay. Now assume that the boundary C is oriented consistently with n. Okay. This means that if you work in the positive direction around C, your head pointing in the direction of n, then the surface will always be on your left. Okay. So next. So what's Stoke's theorem here? So let X be an oriented piecewise smooth surface that bounded by a single closed curve piecewise smooth boundary C. So what is this? With a positive orientation. So you have a boundary C. Okay. And then you bound a oriented surface X. Okay. Let F be a vector field whose components have continuous partial derivative on the open region that contain X. So you see Y continuous partial derivative here. Okay. So Y, let's look at what's the statement here. So the line integral of C. So C is a closed loop. So this is a loop integral. F dot R, this is what? This is word cross time displacement. So you get a word done. It's equal to what? Equals to the double integral of curl dot fx. So this is the what? This, okay. Curl f is what? Is a vector field. Okay. And then you dot with a surface. So this is what? This is flux. So work done around a simple closed curve is equal to the flux over the surface it bounds. Okay. What is curl F? What is curl F? Yeah, what's curl F? Still remember the definition of curl F is defined by what? Gradient operator cross with your vector field. What is this? What is this? Ijk and then del of del x, del of del y, del of del z, and f1, f2, f3. Okay, so you see that if you compute this, right, this is a bunch of partial derivative. So that's why you need a continuous partial derivative here because you want to integrate it. You only can integrate continuous function. Okay. 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 But if f is two variable, right, what is curl f? If f is two variable, what's curl f? If f is just two variable, what's curl f? Curl f is just del f1 del xy minus del f2 over del fx. I think the other way. I think minus is on the other side, like this. Okay, but what is this? This is actually the Green's theorem. Okay, so this is actually the Green's theorem. Okay. But here we are more general. Okay, we can go higher dimensional. So we describe it as a curl F. Okay, we describe it as a curl F. Okay. So in Green's theorem, we have two variables. So when we do the closed loop, right? Okay. Following the right-hand grip rule, the orientation of the surface will be going up. Okay. So this is the positive orientation. Remember last time we did a computation here? Remember we did some computation here? We do the curve for this. Yeah, you see, when we do curve for the two variable case, what do we get? We actually get a direction here for my curve. But inside my Green's theorem, there's no direction here. Why? Because in the flux computation, you need to dot with the unit normal vector. Okay, and the unit normal vector is outward, so it's k. So k dot k, you'll get 1. Okay. Okay. Yeah. Okay. So this Stoke theorem here generalizes the Green's theorem because curl F, I can do it in higher dimensional. Okay, I can do it in higher dimensional. Okay. So this is the mean. Okay, so one is Green's theorem, the other one is the Stoke's theorem. Okay. So Stoke's theorem generalizes Green's theorem. Okay. Yeah. Can understand? This one is stronger. Okay. Yeah. But I don't know this movie. You guys know this movie or not? Don't know. Thor. Oh, okay. I don't know these two characters. First one is Thor. No, it's not Thor. Oh, second one. Okay. Hmm, yeah. Okay. So let's see how we're gonna use this Stokes theorem here. Okay, let's check it on this surface. So let's compute it in two ways. One way, we're gonna loop around the uh, curve that bound the surface, and then the other way, we'll compute the flux. Okay. So verify this Stokes theorem for the vector field here, y I minus xj plus yzk. Okay. If my surface is a paraboloid, z equals to x squared plus y squared, with the circle x squared plus y squared equals to 1 as the boundary, and at the height z equals to 1. Okay, let's compute these two numbers. By Stokes theorem, they should give the same answer. Right. Okay, so let's do the part A first. Okay, so let's compute the work done around this curve. Yeah, let's compute work done around this curve here. So this curve is what? This curve is relatively easy, right? What is this curve? What's the C curve here? Is the circle x squared plus y squared equals to 1 at z equals to 1. Okay, let's try and parameterize this. Right? But how to parameterize this? So how many variables I need to parameterize the line? One, right? Okay, because it's just a line, real line, so you need one variable time t. Okay, so how to parameterize this curve? This is a circle. Okay, circle, remember how to make a circle. Cos t, sin t. Okay, what is the z? The height always 1. Okay, but remember this cos t, sin t, I can keep looping, right? So I need to pick the domain for my t. So what's the domain for my t? It's going from 0 to 2 pi. Okay. Okay, so let's do. So now you can compare what's the difference of line integral and surface integral. Okay, so how to compute this work done here? We need to take integral from 0 to, okay, integral of d of f bar cross. So apply on my line. Just now apply on my surface. Now apply on my line. Dot with. Why is it funny? Okay, apply on the line and then dot with r prime t. Okay, dt. Okay, so what is d? D is 0 to 2 pi. What is f? Am I doing something stupid? Here is the dot product. Okay, what is f? F is y, so sine t minus x become minus cos t, yz become sine t. Okay, and then dot with r prime t. So what's the tangent vector here? What's the tangent vector here? Minus sine t, cos t, and 0. Okay, sine t. Okay, yeah. Okay, so how to compute this? Do this. Okay, so this one we will get minus sine t square t minus cos square t dt. Okay, and then you should get minus 2 pi cos square t, right? Cos square t. Okay, so you are integrating minus 1 actually. Integrating minus 1. So you get 2 pi. But you have a minus, so you get minus 2 pi. Okay, so this is the line integral. Okay, the word done. How about the flux? Okay, how about the flux? So for the flux, what do you need to do? You need to parameterize your surface. Okay, you need to parameterize your surface. So what's your surface? Let's write down the surface first. Z equals to x squared plus y squared. Okay, and then let me see. Bounded above by z equals to 1. Okay, bounded below by z equals to 0. Okay. Yeah. If I don't draw this picture, do you know it? Is it bounded below by 0? Without this picture, can you see or not? This function is z equals to x squared plus y squared. So x squared plus y squared is always positive. Okay, always positive. Yeah. Okay. So if you want to find this why this shape like this, not like cone, please go and do the partial derivative. Okay, in all the direction. You should check that they are the same. Their gradient should be x. I mean, yeah, x if you do fx direction, zx direction, because should be similar to x squared, the curve. Yeah, I think so. Yes. Okay. All right. What do I do now? Okay, I need to parameterize this surface. So let's parameterize this surface here. Okay, so what's the best way to parameterize this surface here? What's the obvious way, at least? I tell you what is z in terms of xy already. Then I need two independent variables. So I just use xy, x, y, and x squared plus y squared. Okay, so this is the easiest one. So this is take note here. Let me take note here. The easiest case for z equals to fxy, the surface. Okay, you can always parameterize by xy and fxy. Okay, because once you have z equals to xy, you have one variable depend on two variables. But to parameterize the surface, you need two independent variables. Then just make x and y independent. Make sense? Yeah. And then the z will depend. This is the easiest case. Okay? If you have z equals to fxy surface. Okay. Okay, remember what do you need for the flux computation? You need to dot with the normal vector. Okay, you need to dot with the normal vector. So what's the normal vector here? You need to compute what is you need to compute what is Rx. cross Ry. Where's Rs cross Ry here? Okay, Rs is what? 1, 0, and 2x. Ry, 0, 1, and 2y. So if you cross this together, you get what? Minus 2x, minus 2y, and 1. Okay? Not that this guy is a positive oriented, because it is a positive k. Okay. Not that in the theorem we need this positivity here. Although I don't play trick inside your exam. Okay. So what's this here? So what's this? So this becomes what? I need to make the surface flat. Okay, become D and dA. But to do that, I have curl F dot with the normal vector. Okay, so compare these two integral here. See the line integral and the surface integral. Okay, what is the similarity? Both of them, I need to make them flat. Okay, both of them, they are living in both line and surface live in 3D. Okay, so for line, I need to reduce to one variable. For surface, I need to reduce to two variables. Okay, by doing that, I need to introduce the tangent vector. Okay, for the one variable case is the tangent vector of your line. For the two variable case is the normal vector of your tangent plane. Okay, normal vector of your tangent plane. Okay, then you take your vector field dot with the normal vector or the tangent vector to get a scalar field, so that you can use multiple integral chapter to do integration. Okay, makes sense. Okay, so in this case here we need curl F. We haven't computed curl F yet. What is curl F here? So let's compute curl F. So curl F is defined to be del cross F. Okay, del cross F. So let's write out quickly. So what is del? Del x, del y, del z. Okay, what is our F? Y minus x and yz. Okay, so if you do this, you should get z, comma 0 and minus 2. Okay. Okay, so we have two vectors now. See, here curl F, here is the normal vector. Then we dot them together. What do you get if you dot them together? If you dot them together, what happens? Not that what happened on my surface. On my surface, what happened to z? My z is x squared plus y squared. Okay, so we need to replace my z now. And let's replace this z because this vector field is happening on my surface. I need to replace the variable on my surface. Okay, altogether I get what? Minus 2x times x squared plus y squared minus 2. Is that okay? Okay, okay. Okay, good. So here is D. But what is D? We haven't decided what is our D yet. Okay, what is controlling our x and y actually? What is our D? How to control our x and y? Any idea? How to control x and y? Here. How to control x and y? X and y can be written in z, but I can control z. So x squared plus y squared is bounded between 0 and 1. Okay. But what is this? What is this? This is a disk. I can do change of variable for me easier to integrate later. So this is a disk. So this is a polar rectangle with radius 0 to 1 and then theta from 0 to 2. Okay, so this is a disk. So how to imagine this? So you should imagine the D is a disk, and the parameterized surface lift the disk up. Okay. Okay, now. So you should imagine the curved surface is like lifting something in the flat domain into some height. Okay, you take a disk and then you lift it up. Okay. Okay. So now you see this is the multiple integral chapter, right? You want to integrate with dx dy, but I change variable to polar dr d theta. So I need to introduce a Jacobian. Okay, so we introduce second Jacobian here. So this will become 0 to 2 pi, 0 to 1 of d dr d theta. So substitute all these change of variable from x from rectangular to polar. X become r cos theta, and then become r squared because x squared plus y squared minus 2. Remember, you have a okay. Yeah. So you can see that once you change variable, this x squared plus y squared become easier to integrate. Yeah. Yeah. So altogether, I think we shouldn't play cheat here. So let's continue. Let's continue. So what should we do? Okay, actually not too hard. So let's do it. So we can split it, right? We can split it. We can split the iterated integral. So split into cos theta part, and then split into the minus 2r to the power 4 dr part. Okay? And then I have an extra minus 2r, right? Correct or not? Right? Wait, let me see. Am I doing some stupid stuff? Yeah, okay. So the minus of 0 to 5, 0 to 1, and then here is 2r. Yeah, d theta like this. Okay, continue. So this part here, what happened? This part, cos theta. After you integrate, you get sine. Sine theta. So sine 2 pi 0, sine 0, 0. Okay, so this part disappear. Okay, something will contribute by this minus 2r here. Okay, so what's this one? What's this? Okay, after you integrate with respect to r, you should get r squared over 2 from 0 to 1, and then d theta d pi. Then you get 1, right? And then you will get minus 2 pi. So previously we also get minus 2 pi. So they agree. Okay. So meaning what? The vector field do the rotational job is equal to the magnetic flux experienced by the surface it bounds. Okay. 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 Last 16 minutes. We have to finish divergence. Okay. By the way, this exercise, right? You can go back and try. If cannot, we come back and do next Thursday. Okay, Thursday. Okay. We still can do exercise together. But we need to go through the theory first. So last one is this last theorem of the year, not of the year. Yeah, of the year. Correct, of the year. Last theorem of the year. You guys have more class to go. Linear algebra, right? Tonight. Tomorrow, probability. And then finish. Okay. So last one, okay. The divergence theorem. Or sometimes we call it a Gauss theorem here. So just now we use loop to bound a surface. Now we use a closed surface to bound a solid. Okay, you can imagine imagine what? You can imagine a ball, okay? A ball, a solid ball. And then the outside is a sphere, okay? It's a closed surface, bound a solid ball, okay? So let E be a solid, simple solid region, and S be the boundary surface. So in your mind, you should imagine something like this. Okay, you have a sphere, X, okay, and then you bound a solid ball inside. We call it E. Even with the positive outward orientation. So you should imagine my surface is like a durian like this. Okay, that's the orientation here. So this orientation here, you see, this orientation is some vector. Vector field also give you vector. So if you have the same direction with orientation, only this vector field will contribute to your integral. I mean, contribute positively. Only when your vector field align positively with your orientation, it will contribute positively to the integral. Because remember, what does surface integral do? You need to dot the vector field with your unit normal vector. Okay, so that's why we call it a divergence. Okay, because if it aligns with the direction of this outward direction of my surface, meaning my vector field is pointing outward, so it's diverged. Okay. Okay, so if my F is a vector field, okay, again, continue with continuous partial derivative, because what we want to do here, we have diff F involved here. So what's the equality here? So if we want to do magnetic flux around the closed surface is equal to the divergence, the triple integral of the divergence in the solid. Okay, so let's look at this picture here. Okay, let's look at this picture here. So suppose this is E. Again, this is a solid object. Okay, and then you have surface. How many surface you have? X2, X1 bottom, and X3 at the side. Okay, so you can compute the magnetic flux over this surface here. Okay, what we do just now. It is equal to the divergence of F. Okay, of the triple integral inside there. Divergence of F is what? Is a scalar field or a vector field? Do you remember or not? Divergence of F. Scalar field or vector field? It's a scalar field. Why? Because remember, diff F equals to what? Equals to the gradient operator dot with the vector field. So if you take two vector dot together, you get what? A scalar. Okay, so that's why you see the volume here, there's no vector anymore. You don't need to do the dot product anymore. Okay, you can straight away integrate it because it's already a scalar field. Okay, you can do the multiple integral we have learned just now. So just now we relate. So Stoke's theorem relates line integral to surface integral. Divergence relate double surface integral to triple integral. Okay, so you go up one dimension, go up one dimension. Okay, so this is the parallelity between Stoke's theorem and divergence theorem. Okay, okay. So one of them. So just now, let me write down what we have just now. So just now we have C, a curve C bounding surface X. Okay, integral of C of F. Okay, dot dr is equals to the surface integral of X of F dot with it's curl F dot with dx. You see? Okay. So you see, for the Stoke's theorems here, so here is Stoke's theorem. For Stoke's theorem, what happened? Both integration involve vector field. Okay. Both of them involve vector field. But divergence, one is vector field, the other one is scalar field. Okay, so it's easier. You don't need to find what normal vector to solid anymore. Okay, nothing. Don't need to do that. Okay. Okay. Let's do one example. Then let's do one example here. Okay, let's do this example here. So we try to look for verify the Gauss theorem for this function, this vector field here, yi plus yj plus zk. Okay, so this is the vector field we have, and then we have this surface here, or the solid here. Okay, what's the solid here? So let's look at the inequality one by one. Okay, so there are two inequality here. So first equality tells you what is x and y. X and y should be bounded by a radius 1 circle. And then z is bounded below by 0. Okay, and then bounded above by this 1 minus x squared minus y squared. What is this? This is almost a sphere. Almost a sphere. Not quite a sphere, but almost a sphere. Okay. Because if it is a sphere, you need a square root. Okay, yeah. Almost a sphere. Okay. So you could draw out the picture something like this. Okay, with the positive orientation like this. So outward. Okay, remember, positive means like a durian. Okay, like a durian. So I have to go outward. All right. Okay, so let's compute these two quantity here. So what is A and B? All right, so what is A? So this is a magnetic flux, not magnetic flux, but a flux, okay, flux over a surface. Okay, so to do flux over a surface, we need to do the parametrization. Okay, we need to parameterize our surface. So how many surface we have here actually? Okay, two of them, x1 and x2. One is this curved surface on the top, the other one is the circle. Okay, so what is x1 here? So x1 satisfies actually z equals to 1 minus x squared minus y squared. Okay. And then, so what is my r here? So r1 here. So this is a z equals to fx function, right? We can simply parameterize as x, y, and then the third coordinate is x minus x squared minus y squared. Okay. And then what's the domain we use here? Okay, we should bound my xy using the unit this again. Okay, but if we're gonna do integration, it is useful to turn this into a polar coordinate. Okay, it's useful to turn this into a polar coordinate. Okay, how about S2? S2 should be easy, right? S2 is just the this. Oh, S2 is just this. So z equal to, so s squared plus y squared equals to 1, z equals to 0. Okay, so this is actually the disk. And this is simply the disk. Okay, it's actually the same as D1 actually. Okay, it's the same as D1. Okay, so how you should imagine this picture here? So you have a disk at the bottom, and then what's this surface? You lift the disk up. Yeah. Okay, you lift the disk up. Yeah, you associate a height to every disk. And then the height is depend on x squared and y squared. All right, so let's do what first? Okay, let's do this. So what is so our integral of del E f dx equals to what? So the integral of x1 f dx plus integral of x2 f dx. Okay. Okay, so to do flux integral, right, you need the normal vector. Okay, you need normal vector. So we need to go and find the normal vector. what's the normal vector we need to use? Let's see here. So what's the normal vector we need to use here? Okay, so let's look at the R1 case. What is R1x cross the R2x? Sorry, R1y. Okay, so what's this guy here? IJK. So R1x, I get 1, 0, minus 2x, and then 0, 1, minus 2y. I think we computed this before. What is this? 2y. Is it 2y? 2y, 2x, 1? What's this? What's this cross product here? That's 2y, 1. Okay, 2x, 2y, 1. Okay, so this is the positive going up, going outward. Okay, so this is good. How about R2? What's the normal vector for R2? AJK. R2 with respect to x, I should get a. So what is R2? So R2x is really just x and y, right? X, y, and 0. Okay, so you got 1, 0, 0, and 0, 1, 0. Okay, what do you get from here? 0, 0, 1. But 0, 0, 1, remember, pointing where? 0, 0, 1 should be pointing up. But on this bottom here, we want it to point down. Okay, so you make sure you want to pick a orientation that's pointing upward. Okay, upward, not up. Up and out is not, it's different. So you want to pick. So positive, so let me remind here. So positive orientation means out, upward. Okay. So you need to use the outward vector, normal vector. Okay. All right. So let's do this computation here. So integrate with respect to x1, f dx. What do we get? We get the integral of d of y x 1 minus x squared minus y squared dot with 2x 2y 1 dn. Okay. And what's this? We need to expand this. We get 2xy plus 2xy again plus 1 minus x squared minus y squared dn. So you see, everything is in terms of x and y. So we need to change variable. Okay, we have to change variable. The disk. Okay, if we change variable, we go into this case here. Okay, once we change variable to rectangular to polar coordinate, we need to multiply by a Jacobian, which is r. Okay, so if you compute all these, you should get a power 2. Okay, so this is for x1. How about s2? What goes to s2? Okay, so if you substitute your vector field into your surface, you will get something like y, x, and 0. Okay, but your normal vector is 0, 0, minus 1. Okay, you keep the outward orientation. Okay, so if you dot these two together, you should get 0. Okay, so all the contribution you get should be pi over 2 only. Okay, only from the first surface. Okay. But how do we do the second computation? Triple integral on diff f. Okay. So what is diff f here? So diff f is delta gradient dot wave function f. So here is del del x, del del y, del del z. Okay, dot wave our f. What is our f? Y, x, and z. So y, x, z. Okay, so what's the thing you get after you dotting these two? The thing that survive is del z, del z. Okay, so you just get one. Right? Okay. Okay. Yeah. So you're doing integral on 1 dv. Let me tell you. Is it okay? I take 5 away. Yeah, last time. Okay, thank you. Okay. Yeah, okay, this. Okay, so how we do this triple integral here? Okay, triple integral. So what to do here? What is the thing we need to integrate over? Okay, let's write down the surface, the solid we want to integrate over. So this we will go back to the chapter of multiple integral. So let's draw our E. X, Y, Z of x squared plus y squared less than equals to 1. Okay. And then our Z is bounded below by 0, bounded above by 1 minus x squared minus y squared. Okay. So, so like this is quite hard to integrate, right? So can we change to some convenient coordinate? There's a circle here, okay, with some height. Okay, we can try cylindrical. Okay, how is cylindrical helpful? First of all, what's the radius here? R from where to where? 0 to 1. Okay, because everything is within the radius 1. Okay, so radius is going from 0 to 1. Okay, how about angle? Angle is going from 0 to 2 pi. Okay, so the hard part should be this height here. But height here is just 0 to 1 minus x squared minus y squared. But what is this? What is x squared minus y squared in r theta form? Is r squared. Okay, so it become 1 minus r squared. Okay. Okay, so we're gonna use the cylindrical mode. So integrate from 0 to 2 pi, 0 to 1, and 0 to 1 minus r squared of r d z dr d theta. So the Jacobian factor for cylindrical is just r. Only for spherical is the r sine t. Okay. Yeah. Okay. So what is this here? So 0 to 2 pi, 0 to 1. Okay, we can split the integral out. Right. So we can split the theta out, d theta out, and then we do the rest. So r squared become rz, right? So rz from 0 to 1 minus r squared. Okay, d what's this? dz. Sorry, dr. Okay. Then what do I get? I just get r times 1 minus r squared. Okay, minus 0. Get this. Okay. And then what is this? 2 pi times r squared over r, 2 minus r to the power 4 over 4 from 0 to 1. Okay, which is 2 times 1 over 4, which is power 2. Okay, and then previously we also get power 2 contribution from the x1 surface. Okay. Okay. Yeah. Any question about the formula? Maybe we will try enough surface example. In next Thursday, maybe we'll try more examples. Okay, yeah. And then in the meantime, you also try out some tutorial question, revision question. In particular, first thing priority you should do is actual example. Second thing is the revision question. And then third thing, you only go to tutorial because tutorial, I mean, textbook question is quite hard. And then you can do those. And then if you meet any problem, you bring on next Thursday. Okay. Okay. Yeah. How should we take photo here? Go outside. Okay. If go outside. Okay, go outside. What?
靠边
Thank you.
有时候剪开中间，
剪开中间
沿着这个线
，and then
剪开，
and then
然后它会变成一个大的圆圈，
会变成大的圆圈，也就是说变成一个真的圆圈。
是这样？
哦，
哦，
等下试一下，等下试一下，等下试一下。
我这个有简单吗？这个简单。
剪那个中间那条线。